Trees standing at sunrise, bridge spanning a river by sunset. 100 feet long, 40 feet high, built entirely from timber cut that morning. Green wood, still wet with sap, still heavy with moisture, wood that hadn't been seasoned or dried, wood that conventional wisdom said would warp and crack and fail under load. And yet, there it stood by nightfall, ready to carry locomotives weighing tens of tons across a river that had been an impassable barrier 12 hours earlier. 500 workers moving like a military operation, cutting trees, dragging logs, shaping timbers, raising massive wooden structures using nothing but axes, saws, ropes, and determination. This was America during the Civil War and the railroad expansion era, and speed mattered more than perfection, progress mattered more than polish, and getting the bridge up today mattered more than making it last forever. This was the 1860s, and America needed bridges fast. The Civil War was destroying railroad infrastructure across the South. Sherman's march burned bridges. Confederate guerrillas dynamited trestles. Both armies tore up tracks and demolished bridges to deny their enemies transportation routes. And as fast as bridges were destroyed, they had to be rebuilt because railroads were the arteries of war. Supplies moved by rail. Troops moved by rail. The army that could rebuild bridges faster could move faster, supply faster, fight more effectively. Speed wasn't just advantageous, it was survival. Could you really cut trees in the morning and have them supporting a railroad bridge by evening? Could you build structures strong enough to carry locomotives using wood that was still green, still full of moisture, not properly seasoned? And could you do it with crews of 500 men, most of whom had never built a bridge before, working from rough plans or no plans at all, improvising solutions on the spot? The answer is yes. The evidence is in the records of the United States Military Railroad, in the journals of Hermann Haupt and other engineer officers, in photographs showing massive timber bridges built in days where conventional engineering said it should take months. Before we get to the bridges themselves, you need to understand why green wood was used and what that actually meant for construction. Because this wasn't just about building quickly, this was about building with a material that behaved differently than anything engineers were accustomed to working with. Seasoned lumber, wood that's been cut and allowed to dry for months or years, is what you'd normally use for construction. As wood dries, it shrinks, it warps, it develops cracks. But once it's dry, it's stable. It won't change dimension significantly. It's predictable. Seasoned wood is what you use when you want structures that will last decades. But seasoning takes time. You cut a tree, mill it into timbers, stack it to dry with air circulation, and wait. 6 months minimum. A year is better. For large timbers, 2 years. The Union Army didn't have 6 months. They didn't have a year. They had days, maybe a week if they were lucky. So they used green wood, trees cut in the morning, shaped into timbers, and installed in structures by evening, wood that was still heavy with sap and moisture, wood that would shrink as it dried, wood that would crack and check and warp, but wood that was available immediately and could be worked with hand tools. Green wood has properties that actually made it useful for emergency construction despite its instability. It's softer than dry wood, which means it's easier to cut and shape. An axe bites deeper into green wood. A saw moves through it faster. That mattered when you were shaping hundreds of timbers by hand in a day. Green wood is also more flexible than dry wood. It can bend slightly without breaking, which is useful when you're fitting pieces together that aren't perfectly cut or when the structure settles under load. And perhaps, most importantly, green wood is available everywhere there are forests. You don't need sawmills. You don't need supply chains. You just need trees and workers with axes. But using green wood introduced specific engineering challenges that had to be understood and compensated for. The moisture content of freshly cut wood varies by species, but typically ranges from 40 to 60%. That means a green oak log weighing 1,000 pounds contains 400 to 600 pounds of water. As the wood dries in the structure, that water will evaporate and the wood will shrink. The shrinkage isn't uniform. Wood shrinks more across the grain than along it. A 12-inch square beam might shrink to 11.5 inches across, but retain its length almost exactly. This differential shrinkage creates stresses in joints. Imagine a mortise and tenon joint cut tight when the wood is green. The tenon fits snugly into the mortise. As both pieces dry, they shrink. But they don't shrink at the same rate or in the same direction. The joint loosens. In a bridge with hundreds of such joints, the cumulative loosening can cause the entire structure to become unstable. Engineers compensated by using mechanical fasteners, iron bolts, spikes, pins that could handle movement. These fasteners were expensive and had to be transported to remote bridge sites, but they were essential for making green wood structures functional. The checking and cracking of green wood as it dried was another concern. As wood dries, internal stresses develop. The outer surface dries faster than the interior, creating tension. The wood relieves this tension by cracking. The cracks are called checks, and they're often radial, running from the outer surface toward the center. In structural timber, checking reduces strength. A beam with deep checks across its width is weaker than an identical beam without checks. But checking is inevitable with green wood. You can't prevent it. You can only account for it in design. Engineers dealt with checking by overbuilding, using timber larger and stronger than strictly necessary, so that even after checking reduced strength, adequate load capacity remained. A beam that should theoretically be 8 inches square might be specified as 12 inches square to account for future checking. This overbuilding increased the amount of timber needed, which meant more trees to cut and more weight to handle. But it was necessary to ensure the structure would remain safe as the wood dried. The weight of green wood was itself a logistical challenge. A dry Douglas fir log, 12 inches in diameter and 20 feet long, weighs about 400 pounds. The same log, when green, weighs close to 700 pounds. That extra 300 pounds made every aspect of handling more difficult. More workers needed to lift each timber, more strain on ropes and tackle, more effort to position components. And the workers handling this green timber were doing it for hours each day, moving hundreds of pieces. The physical toll was enormous. The construction technique for these emergency bridges was developed and refined during the Civil War by the U.S. Military Railroad, particularly under the direction of Herman Haupt, a civil engineer who'd worked on railroads before the war and who became responsible for railroad operations for the Union Army. Haupt understood that traditional bridge-building methods were too slow for wartime needs. He developed standardized designs that could be built quickly by relatively unskilled labor using materials found on site. The basic design was a timber trestle, vertical wooden posts driven into the riverbed or resting on cribwork foundations, with horizontal beams spanning between the posts, and the railroad track laid on top of the beams. Simple in concept, brutally demanding in execution. A typical emergency railroad bridge might be 100 feet long and 40 feet high. That required dozens of vertical posts, each one a log 12 to 18 inches in diameter and 50 feet long. It required hundreds of horizontal beams and cross braces, and all of it had to be cut, shaped, transported to the site, and assembled in a matter of days. The process started with selecting timber. A crew would go into the nearest forest, often just the forest adjacent to the bridge site, and mark trees suitable for the various components. Posts needed to be straight, tall, and relatively free of large branches. Beams could be shorter, but still needed to be straight. The felling crews would cut the marked trees, working with crosscut saws and axes. A good 2-man crew could fell and limb a tree in about an hour. Scaling that up, a 100-man felling crew could prepare timber for a major bridge in a single day. The logs would be dragged from the forest to the bridge site using horse or ox teams. Speed mattered more than preserving the wood, so logs were dragged directly over the ground, getting scarred and damaged, but arriving at the construction site ready to use. As logs arrived, they'd be sorted by size and quality. The best straight logs would be set aside for posts. Smaller logs would be designated for cross-bracing. Anything with major defects would be used for temporary works or discarded. The shaping of the timbers was done on-site with hand tools. Axes to square the logs where necessary. Adzes to create flat surfaces where beams would join. Augers to drill holes for wooden pins or iron bolts. There was no time for precision work. The timber was shaped enough to be functional and no more. If a beam wasn't perfectly square, it didn't matter as long as it would bear the load. If the surfaces weren't smooth, that was fine. This was engineering for function, not appearance. The assembly of the bridge happened in sections. The crew would build the first bent. That's a section consisting of vertical posts connected by horizontal beams. The posts would be positioned and braced temporarily. The cap beams would be lifted into place and secured. Then the next bent would be built, and horizontal stringers would connect the two bents. Then another bent. Section by section, the bridge grew across the gap. The speed of construction was extraordinary by modern standards. A crew of 500 men, well organized and working with good materials, could build a 100-foot bridge in 3 to 5 days. The construction of the Potomac Creek Bridge, one of the most famous examples, took just 9 days for a structure that was 400 feet long and 80 feet high at its highest point. The bridge used approximately 2 million board feet of timber, equivalent to cutting down about 400 large trees, and was built by about 400 men working around the clock in shifts. The Potomac Creek Bridge deserves detailed attention because it was photographed extensively and documented in military reports, giving us unusual insight into emergency bridge construction. The bridge was built in May 1862 under Herman Haupt's direct supervision. The site was about 60 miles south of Washington, crossing Potomac Creek, which had been bridged before the war, but the original bridge had been burned by Confederate forces. Haupt arrived at the site on May 5th with a workforce of about 400 men, most of them civilian laborers hired specifically for this project. He had no prepared drawings. Instead, he had a mental design, a standard trestle pattern he'd developed that he adapted to the specific site conditions. He paced off the distance to be bridged, noted the height required, and calculated how many bents would be needed. Then he organized the workforce into specialized teams. The timber cutting crew, about 100 men, was sent into the forest on both sides of the creek with instructions to fell, delimb, and rough cut every suitable tree they could find. Haupt specified minimum dimensions. Posts needed to be at least 12 inches in diameter and 40 to 60 feet long, depending on their position in the structure. Crossbeams needed to be at least 8 inches square. The cutting crews worked in pairs, and each pair responsible for felling and processing specific trees. By the end of the first day, over 200 trees had been felled. The hauling crews, another 100 men with ox teams, dragged the logs from the forest to the creek bank near the construction site. The logs were sorted by size and quality as they arrived. The straightest, longest logs were marked for main posts. Shorter logs went for cross-bracing. Logs with curves or defects that would have made them unsuitable for primary structural members were designated for temporary works, scaffolding and supports needed during construction, but not part of the final structure. The shaping crews, skilled carpenters and experienced railroad workers, worked on the logs as they were sorted. Using broad axes and adzes, they would square critical joints, flatten surfaces where timbers would bear against each other, and cut notches where pieces would connect. This work required skill and experience. A carpenter who knew what he was doing could square a joint in minutes. An inexperienced worker might take an hour and still not get it right. The assembly of the bridge started at both banks simultaneously and worked toward the center. The first bent on each side was built on solid ground, which was easier than building in the creek. Workers would position posts vertically, brace them with temporary supports, and then lift the cap beam into place. The cap beam, the horizontal timber that connected the tops of the posts, might weigh 800 to 1,000 pounds. Lifting it required block and tackle systems operated by teams of workers pulling on ropes. Getting the beam positioned and secured could take hours. With the first bent in place on each side, the crews would build the next bent closer to the center of the span. Horizontal stringers would connect the bents, creating a framework. As the framework extended over the water, workers would stand on the partially completed structure, working at heights that increased as the bents grew taller. There were no safety harnesses. Men worked on narrow beams 40 or 60 feet above the water, maintaining balance through experience and concentration. Falls were common. Several workers fell during the Potomac Creek construction. Most survived because they fell into water rather than onto rocks or the ground, but water at 40 feet can hit like concrete if you land wrong. At least one worker died from injuries sustained in a fall during the construction. The final bent, meeting in the middle of the span, was the most difficult. The crews from both sides had to align their work so the two halves would connect properly. This required careful measurement and constant adjustment. If the bents were even slightly misaligned, the stringers wouldn't fit, and the entire section would have to be repositioned. Haupt personally supervised this final connection, using surveying instruments to check alignment and directing workers to make small adjustments until everything lined up. The decking, the surface on which the rails would be laid, went on last. Workers would lay planks across the stringers and spike them down. The planking was typically 3-inch thick boards laid perpendicular to the direction of travel. The boards were spiked every few feet to prevent shifting. Then the rails were laid on top of the planking and spiked to cross ties that had been integrated into the decking structure. The Potomac Creek Bridge was completed on May 14th, 9 days from the start of timber cutting to trains crossing. President Lincoln visited the bridge shortly after its completion and was reportedly amazed, stating, according to witnesses, that it was the most remarkable structure human eyes have ever rested upon. That man Haupt has built that structure of nothing but bean poles and corn stalks. Lincoln's quote, while exaggerated, captured the apparent impossibility of the structure. Massive timbers that looked impossibly slender supporting heavy locomotives. Another remarkable example of emergency bridge construction was the Chattahoochee River Bridge in Georgia, built in 1864. This bridge was even more challenging than Potomac Creek because it was built under active military conditions with Confederate forces nearby and potentially hostile. The bridge was 460 feet long and 78 feet high, crossing the Chattahoochee River, which was a significant military obstacle. The construction supervisor for the Chattahoochee Bridge was Colonel William W. Wright of the U.S. Military Railroad. Wright had learned rapid bridge construction techniques from Haupt and had supervised multiple bridge projects during the Atlanta campaign. The Chattahoochee Bridge was built in just 4.5 days by a workforce of about 500 men, and including soldiers detailed from infantry units to provide additional labor. Wright's approach was even more aggressive than Haupt's. He organized the workforce into 3 shifts, working around the clock. While the day shift was building the bridge, the night shift was cutting and preparing timber by lantern light and firelight. The hauling and shaping continued continuously. Workers who finished a 12-hour shift would sleep for 6 hours and return for another shift. The pace was brutal, but the bridge was critical to Sherman's advance and speed was paramount. The Chattahoochee Bridge was built entirely from green pine, Georgia yellow pine cut from forests on the north bank of the river. Pine was not ideal for bridge construction. It was softer and less durable than oak or other hardwoods, but it was available in abundance and could be worked quickly. Wright compensated for the weakness of pine by using larger timbers, posts that were 16 to 18 inches in diameter instead of the 12-inch posts typically specified. The bridge was completed on July 9, 1864, and Sherman's army crossed it the following day. The bridge remained in service for 3 months before being burned by retreating Confederate forces in October. During those 3 months, it carried thousands of soldiers, hundreds of wagons, and numerous artillery pieces. Despite being built in less than a week from green pine, it functioned adequately for its purpose. But let me be clear about what 3 to 5 days actually meant for the workers. This wasn't an 8-hour workday. This was sunrise to sunset, on 12 to 14 hours of continuous heavy labor, felling trees, dragging logs, lifting timbers that weighed hundreds of pounds, positioning posts, driving pins, hauling ropes, all of it done manually, all of it done at a pace that left no time for rest. The physical demands of this work were extreme by any standard. Consider a typical day for a worker on a bridge construction crew. You'd wake before dawn in a tent or rough barracks. Breakfast would be simple: bread, salt pork, coffee. Then to the work site. If you were on a felling crew, you'd walk to the forest carrying your saw and axe. You'd work with a partner cutting trees all morning. Each tree required cutting a notch on one side to direct the fall, then sawing through from the other side. A good crew could fell a tree in 45 minutes to an hour. You'd fell 4 or 5 trees before the midday break. The midday meal was brief, 30 minutes, maybe an hour, more bread, more salt pork, water or weak coffee. Then back to work. More trees to cut. Or if you'd met your quota, you'd start delimbing, removing branches from the felled trees using an axe. Delimbing was less skilled than felling, but just as physically demanding. You'd swing an axe thousands of times per day. Your hands would develop calluses. Your shoulders and back would ache. But you kept working because stopping meant you weren't earning. If you were on a hauling crew, your day was different but no less demanding. You'd work with ox teams, dragging logs from the cutting site to the bridge. Each log had to be chained to the team, which meant working close to the oxen, getting kicked or stepped on occasionally. The oxen would pull, and you'd guide them, keeping the log from catching on obstacles. A log might weigh 1,000 pounds or more. If it caught on a stump or rock, you'd have to stop the team, free the log, and start again. You'd make dozens of trips per day, each one requiring careful navigation through forest that was often rough and obstacle-filled. If you were on the assembly crew, you had perhaps the most dangerous job. You'd be working on the bridge structure itself, often at height. You'd position timbers, drive pins, secure joints. The work required strength and precision. A timber positioned incorrectly could compromise the entire structure. A pin driven at the wrong angle might not hold. And you were doing this while standing on narrow beams dozens of feet above the ground or water, each with other workers around you also moving timber and working with tools. The danger was ever present and accepted as part of the work. Workers carried insurance in the form of caution and experience, but accidents happened regularly. Falls from the structure, being struck by falling timber, getting crushed between components during assembly. The injuries range from minor, cuts, bruises, sprains, to catastrophic, broken bones, severe head injuries, death. Among the workers was a man named Patrick Donovan, an Irish immigrant who worked on bridge construction from 1862 to 1864. Donovan kept a diary, portions of which are preserved in a historical collection at the Library of Congress. His entries described the work in stark terms. From June 1863. Today we built 70 feet of bridge structure. I worked on the assembly crew, positioning cap beams. The work is terrifying. We are 40 feet above the water, standing on beams that are barely wide enough for our feet, lifting timbers that could crush us if they fall. 3 men fell today. 1 broke his arm, 1 broke his leg, 1 fell into the water and was pulled out by men in a boat. We kept working. The bridge must be finished. Donovan's diary also records the toll the work took on the men. From August 1863. My hands are destroyed. The calluses have calluses. My back is in constant pain. I am exhausted beyond measure. But the pay is good, $2 per day when the work is available. I am sending money home to my family in Ireland. They depend on it. So I continue working despite the pain and the danger. Donovan was killed in September 1864 when a bridge he was working on collapsed during construction. The accident report states that 6 workers were on the structure when a key support failed. The section collapsed, dropping the workers 40 feet to the ground. 4 died immediately. 2 survived with severe injuries. Donovan was 31 years old. His diary ends the day before the accident with a routine entry about the day's work and his hope that the bridge would be finished soon so we could move to the next project. Another named individual whose story survives is William Tecumseh Sherman's personal railroad engineer, a man named Colonel Orlando Poe, who supervised multiple bridge construction projects during the Atlanta campaign and Sherman's March to the Sea. Poe's official reports and personal letters provide insight into both the engineering challenges and the human cost of rapid bridge construction. In a report from July 1864, Poe wrote, "We have built 17 bridges in the past month, ranging from simple trestles of 30 feet to major structures of several hundred feet. The speed of construction is extraordinary, but comes at a cost. We have lost approximately 40 men to accidents during this period. Falls, crushing injuries, and one case where an entire bent collapsed during assembly, killing 5 workers. I regret these losses, but the military necessity of maintaining the railroad to supply General Sherman's army cannot be denied." Poe's letters to his wife are more personal. and reveal the emotional burden of supervising work that regularly killed men. In a letter from August 1864, "I am responsible for the deaths of men who are building the bridges I design. I know the work is dangerous. I try to enforce safety precautions, but the pace of work makes perfect safety impossible. We are building too fast, using green timber that is unpredictable, working men to exhaustion. And yet we must continue because the alternative is to leave Sherman's army without supply lines, which would cost far more lives than the bridge accidents do." The organization required for this speed was military in nature because it was literally organized by military officers. The workforce would be divided into specialized crews: felling crews in the forest, hauling crews moving logs to the site, shaping crews preparing timber, assembly crews positioning and securing components. Each crew had specific tasks, and the crews rotated through positions to prevent total exhaustion. But even with rotation, the work was crushing. By the end of a day, men were too tired to eat. They'd collapse in their tents and sleep until the next shift started. The danger of this work was considerable. You were working with large timbers moving fast. A log being dragged by an ox team could crush you if you got in its path. A timber being lifted into place could fall. The temporary bracing holding up partially completed sections could fail. Men working on high sections of the bridge could fall. And because everything was happening at speed, there was less time to check safety, less time to ensure everything was secure before moving to the next task. There are documented casualties from bridge construction work during the Civil War, though the records are incomplete. In March 1863, a worker named James Sullivan was killed at a bridge construction site near Fredericksburg when a cap beam being lifted into place slipped from its ropes and fell on him. The beam weighed approximately 800 pounds. Sullivan was crushed instantly. His body was removed and the work continued within the hour. The military railroad kept a log of casualties. Sullivan's death is listed alongside dozens of others killed in accidents during bridge construction. Another documented incident occurred in July 1864 at a bridge site in Georgia. A partially completed bent collapsed while workers were securing the cap beam. The posts had been positioned in soft soil without adequate foundation, and under the weight of the beam and the workers on the structure, the post shifted and the entire bent fell. 6 workers were on the structure when it collapsed. 3 were killed in the fall or crushed by falling timber. 3 survived with injuries ranging from broken bones to severe bruising. The construction supervisor, Lieutenant Edward Morris of the U.S. Military Railroad, noted in his report that the collapse was due to inadequate founding in marshy ground, but also noted that there had been insufficient time to prepare proper foundations given the urgent military necessity of completing the bridge. The temporary nature of these bridges was understood from the start. They weren't built to last. They were built to function long enough to serve their immediate purpose, usually moving an army or supplies across an obstacle. The green wood would shrink as it dried, joints would loosen, the structure would settle and shift. Some bridges built from green wood would last for months before needing major repairs. Others would start showing problems within weeks. But the fascinating thing is that some of these temporary bridges lasted far longer than intended. The Potomac Creek Bridge, built in 9 days from green wood, remained in service for over a year. The bridge visibly sagged and creaked as trains crossed it. Engineers would inspect it and pronounce it unsafe. But it kept standing, kept carrying trains, defying expectations. It was finally replaced in 1864 with a more permanent structure, but the fact that an emergency bridge built from green wood in 9 days lasted over a year speaks to both the skill of its construction and the inherent overbuilding of the design. Hermann Haupt, the chief engineer who developed many of these rapid construction techniques, was well aware of the limitations of green wood construction. His written instructions to subordinate engineers are preserved in the military archives, and they're remarkably pragmatic. In one memo from 1862, he writes, "The bridges we construct are not permanent works, they are expedients. Build them strong enough to carry the trains we need to move, no stronger. Use green timber because we have no choice. Understand that the structures will deteriorate and plan to replace them when time permits. But build them now, build them quickly, and build them adequately for present needs. That philosophy, good enough for now, was antithetical to traditional engineering practice, which emphasized durability and permanence. But it was exactly what the situation required. The alternative to a bridge that might last 6 months was no bridge at all, which meant armies couldn't move, supplies couldn't get through, and military operations would fail. The techniques developed during the Civil War for emergency bridge construction had applications beyond wartime. The Transcontinental Railroad, built from 1863 to 1869, used similar methods for rapid bridge construction across the West. Many bridges were initially built from green wood using emergency construction techniques, then replaced with permanent structures later. The Dale Creek Bridge in Wyoming, built by the Union Pacific in 1868, was a massive timber trestle 650 feet long and 130 feet high. Built in about 30 days using timber cut from the surrounding forest, it used approximately 4 million board feet, roughly 800 trees, assembled by about 500 workers. Samuel Reed, the construction supervisor and Union Pacific civil engineer, kept journals describing the process. In June 1868, he wrote, "We are cutting timber as fast as we can find suitable trees. The men are working admirably despite the altitude and difficult conditions. We are using green wood throughout, which concerns me greatly as I have no experience with its long-term behavior in structures of this magnitude. But we have no choice. The railroad must advance." The Dale Creek Bridge stood for 13 years before being replaced with an iron bridge in 1881. Despite being built from green wood in 30 days, it carried trains across a 130-foot-deep canyon for over a decade. And the bridge sagged noticeably over the years, but kept functioning until a permanent structure could be built. The workers who built these bridges were a mix of soldiers, freed slaves, immigrants, and experienced railroad workers. During the Civil War, the U.S. Military Railroad employed both military personnel and civilian contractors. The civilian workers were often Irish immigrants or free black men from the North who took the work because it paid reasonably well and provided some measure of security during wartime. The pay was about $2 per day for laborers, $3 to $4 for skilled workers like carpenters. That was comparable to other industrial work, but the conditions were harder and more dangerous. The workforce for the Western Railroad bridges was similar, primarily Irish and Chinese immigrants, with some Civil War veterans mixed in. These workers would move from bridge to bridge as construction progressed, becoming skilled at the rapid construction techniques through repetition. Some workers became specialists, known for their ability to position posts or lift heavy beams or tie joints quickly and securely. One such worker was Thomas McKenna, an Irish immigrant who worked on railroad bridge construction from 1864 to 1870, first on military bridges during the end of the Civil War, then on the Union Pacific. McKenna's name appears in multiple construction reports and payroll records, always noted as a head carpenter or section boss. In a letter he wrote to his brother in Ireland in 1867, preserved in a historical collection, McKenna describes the work. "We are building bridges faster than you would believe possible. Ash trees are cut in the morning, and by nightfall they are part of a structure spanning a river. The work is hard beyond measure. My hands are covered in calluses and splinters. My back aches from lifting timbers. But the pay is steady, and I'm saving money. America is a hard land, but it offers opportunities that Ireland never could." The tools available for this work were primitive by modern standards. Crosscut saws to fell trees and cut timber to length, axes and adzes to shape wood, hand augers to drill holes, wooden mallets and steel wedges to drive wooden pins, block and tackle systems with rope to lift heavy timbers. That's essentially it. No power tools, no cranes, no mechanical advantage beyond simple machines, pulleys, levers, inclined planes. Everything was done by human muscle or animal power. The efficiency achieved with these simple tools was remarkable. A skilled crew with good tools and good timber could cut, shape, and install a bridge component faster than untrained modern workers with power tools could accomplish the same task. The difference was practice and necessity. These men did this work every day. They developed techniques and rhythms. They knew exactly how to position themselves, how to coordinate their movements, how to maximize efficiency. And they worked with an intensity born of necessity. The bridge had to be finished. There were schedules to meet and consequences for failure. The logistics of supporting 500 workers at a remote bridge construction site were themselves formidable. Food had to be provided, thousands of calories per day to sustain heavy labor. Water had to be supplied. Shelter had to be arranged. Tools had to be maintained. Medical care had to be available for the common injuries. Both the Army and railroad companies relied heavily on camp followers, cooks, launderers, sutlers selling supplies, sometimes families of workers. A bridge construction site with 500 workers might have a total population of 700 when support personnel were included. The speed of bridge construction created opportunities for profit and corruption. Contractors who supplied timber or labor could inflate costs knowing the Army or railroad needed the work done immediately and had little time to verify prices. There are documented cases of contractors charging for timber that was never delivered or for workers who never existed. The oversight was minimal because the engineers supervising construction were focused on getting the bridge built, not on financial accounting. One documented case involved a contractor named William Harvey who supplied timber for bridges in Virginia during the winter of 1863. Harvey charged for delivering cut timber to bridge sites, but investigation later revealed that much of the cut timber was actually standing trees that Harvey marked as delivered, but never actually felled or transported. The fraud was discovered when bridge construction crews arrived at sites expecting to find stockpiled timber and found nothing. Harvey had been paid approximately $20,000, $600,000 in modern currency, for timber that was never delivered. He was prosecuted, but the money was never recovered. The environmental impact of this rapid bridge construction was significant in localized areas. A single large bridge might require cutting 400 to 800 trees. Those trees came from the forest surrounding the bridge site, creating clear-cut areas. The logs would be dragged through the forest, creating paths and disturbing undergrowth. The construction activity would drive away wildlife and disturb streams. In the context of the vast American forests of the 1860s, this impact was minimal. But in specific locations, the environmental damage was noticeable. Some bridge sites were essentially strip-mined of timber. The area around the Dale Creek Bridge site in Wyoming was heavily logged to provide timber for the bridge. Photographs from the 1870s show a landscape of stumps surrounding the bridge. The forest eventually regrew, but the immediate impact was severe. Similar patterns existed at other major bridge sites. Anywhere a massive structure was built from local timber, you'd find a denuded landscape. The transition away from green wood bridge construction came with the rise of iron and steel fabrication in the 1870s and 1880s. Iron bridges were more expensive initially, but lasted far longer and required less maintenance. Railroad companies that had initially built wooden trestle bridges gradually replaced them with iron structures. By 1890, most new railroad bridges were being built from iron or steel. The wooden bridges were relegated to temporary or secondary use. But the knowledge and techniques developed during the rapid construction era didn't disappear entirely. The methods for quickly building wooden structures were used for construction camps, industrial buildings, and temporary facilities well into the 20th century. The ability to go from standing trees to functional structure in a day remained valuable in situations where speed mattered more than permanence. Today, very few of the Civil War-era emergency bridges survive. They were temporary by design and were replaced as soon as resources allowed. The transcontinental railroad bridges mostly met the same fate. What remains are photographs, engineering reports, and occasional foundation stones or timber fragments. The legacy of this rapid construction era is less about the specific bridges and more about what they demonstrate about human capability. 500 workers with hand tools could build a 100-foot bridge in days. They could cut trees in the morning and have those same trees supporting locomotives by evening. They did it through organization, skill, and relentless physical labor. They did it because the alternative, not building the bridge, was unacceptable. The bridges themselves were often rough, sometimes barely adequate, occasionally dangerous. But they worked. They allowed armies to move. They allowed railroads to be built across a continent. They made possible things that conventional engineering said would take months. And they did it with green wood, with trees that were still wet with sap, with timber that would crack and warp and shrink as it dried. The engineers knew the limitations. They built anyway. And somehow, improbably, it worked. If you think about the comparison to modern construction, it's humbling. Today, we have cranes, power tools, computer modeling, engineered materials. A modern bridge takes months or years to build with all these advantages. The workers of the 1860s had axes and ropes and determination, and they built bridges in days. The structures weren't as good. They didn't last as long, but in the context of their time and needs, they were exactly what was required. The men who built these bridges, Thomas McKenna standing on a partially completed trestle in Wyoming, James Sullivan crushed by a falling beam in Virginia, the hundreds of anonymous workers whose names don't appear in any record. They accomplished something that deserves recognition. They built infrastructure that made history possible. They did it with primitive tools and impossible timelines. They died doing it. And for the most part, they've been forgotten. The trees they cut are long gone, grown back as new forest. The bridges they built are gone, replaced by permanent structures or abandoned entirely. What remains is the knowledge that it could be done, that you could cut trees in the morning and have a bridge by evening. That green wood, despite all its limitations, could serve when that's all you had. That speed and necessity could overcome conventional limitations when the stakes were high enough. That's the legacy of the emergency bridge builders of the 1860s. They proved that the impossible was just difficult, and difficult was something that could be overcome with enough workers and enough determination.